So in general, when you do a hypothesis test, you have what's called a null hypothesis, which is some statement about the population parameter. That allows you to create a theoretical density curve that's true under those conditions. You then create a test statistic that's based on your sample that you collected, your statistic, and then you test against it. You find a probability that you would have gotten something as extreme as you did in that test statistic, which is the type of stuff we were doing with our normal distribution in this case, or under whatever density curve you have. It's the area under the curve is where these numbers come from, but they're probabilities. What they are is a probability that you would have gotten this test statistic or something as extreme as this test statistic, less than or greater than or not equal to, which would be less than or greater than. So it's a one-sided or a two-sided test. And the p-value is the probability that that occurs. In this section, we're starting with the z-test. Okay, so we're talking about a single population and a single population mean. Our test statistic would be the z-score for the sample mean. Remember, a z-score was x minus mu over sigma, but it's your statistic minus your parameter divided by the standard deviation of your statistic. So for x bar, we're going to do x bar minus mu sub 0, we're subtracting what we're going to assume in the hypothesis that mu is equal to, this number mu sub 0, which is whatever it is in the particular problem or the situation. And we divide by the standard deviation of x bar, which is sigma over square root of n. So if you have to compute that test statistic yourself, there's the formula. It's x bar, your sample mean that's found in the data, minus mu sub 0, which is what you're assuming mu is in the null hypothesis. That's how the whole process works. We're going to assume mu is equal to a certain value and then find a probability based on that. And if it's really low, we have good evidence that mu was not equal to that value. And then our alternative hypothesis could be a greater than, a less than, or a not equal to. If it's a less than or greater than, we call that a one-sided test because when you look at the picture, you're finding the area in one tail on the standard normal distribution. If it's a not equal to, it could be greater than or less than, and it's a two-sided test. So that's the z-test and how it works. There's a way to do it on the calculator, plus we could find the z-score and use normal CDF to find these probabilities as well if we wanted to do it that way. So example 2, we're going to go back to our situation we had in example 1 where they were doing job satisfaction, and I'm going to throw in some numbers so that we can actually compute a p-value here. So recall the job satisfaction example we had before where they were doing machine-paced versus self-paced, and they measured the difference between those. And we had the null hypothesis that mu was 0, that the average difference was 0 versus not equal to. So the company was comparing job satisfaction of self-paced versus machine-paced. Suppose the job satisfaction difference scores follow a normal distribution with a standard deviation of sigma equals 60. Data from 18 workers gave a sample mean score of 17. Okay, so that's a small sample. We only have 18. It's less than 30. So it's important that we're assuming the distribution was normal to start with, so we can assume x bar would be normal. Remember, if your original population is not normal, you need larger samples, larger than 30 or so. So we had our hypothesis that mu was equal to 0 because mu was the difference between the scores. We want to see if there's no difference versus there is a difference. Mu is not equal to 0. So one way to do this, the long way, if we're not just going to use z-test on our calculator, we could compute the z-score and then find a probability to test against this. So we do our test statistic, our p-value, and then make a conclusion. So I am just going to do it with the z-test. That's the way you can do it on the tests in class. By the time we get to a test, we'll have multiple procedures, so part of it is you got to decide which is the correct procedure to use. Here we're given sigma and we're looking at one mean, so that's the z-test. Okay? And then we got to run it, find the information, make the correct interpretation. I have the screenshots of the calculator, but I'm going to pull the actual calculator in here. So if you didn't have this particular type of calculator, you could compute the test statistic yourself. You could just do x bar, which was 17. The mean was 17. Minus 0. Mu sub 0 is 0. We're doing the hypothesis that mu is 0. We would divide that by sigma over square root of n. Let's see, sigma is 60, and we have a sample size of 18. So divided by 60 over square root of 18. Okay. And we have that the test statistic is 1.2, And then we would have to set up a two-sided picture and find the probability that either z is greater than 1.2 or less than negative 1.2. So that's how you would do it if you were going through it by hand. But on my calculator, I can do stat, go to the test menu, and number 1 is the z-test. All of these things, the first line is your input a set of data or do you have the statistics? If you have the actual data, you put it in a list and you choose that. Otherwise, you choose stats. And then it's going to ask you for all the necessary information. You have to tell it, in your null hypothesis, what are you assuming mu is equal to? Well, it's 0 on this problem. And then what is sigma? For a z-test, you have to know sigma. It's given to us to be 60 in this problem. What is x bar? That's the mean from the sample, which is 17. And then n, the sample size was 18. The data came from 18 workers. And then you have to pick your null hypothesis. Mu is either equal, not equal to, less than, or greater than. We're going with not equal to mu sub 0, which is 0 here. And then you have the option to calculate or draw. They'll both give you the same information. If you draw, it'll show you the picture of what you're doing. You might want to, I was doing some algebra here. Let me clear that out. Let me redo it. So stat, test, z-test. It's got everything stored. I'm going to go down to draw. It will draw the picture of what it's doing. It's the standard normal distribution, and it's finding, it shows you that z is the same thing I had a minute ago, about 1.20. So on this graph, that would be 1.20, negative 1.20, and then it's finding the area to the left and the right of that, and adding those two together. It's doing the total shaded area there is 0.23. This is called a two-sided test because we're getting our area from two sides. So our p-value is about 0.23, which is quite large. Okay, and any time it's not given, let's go with 5%. Okay, that's the most common. Our p-value is much more than 5%. There's a 23% chance that the difference we observed in our sample was just due to random sampling, so we don't have strong evidence that there is a difference, that mu is not equal to 0, and we would fail to reject. So if you do draw, it'll give you the z and the p that way, the test statistic and the p-value, and show you the picture of what you're doing, which is kind of nice. It has to round to fit it on that screen, especially if your p-value goes into like scientific notation. It may say it's 0. It's almost never 0 if you look at it and get more digits. So if you do calculate, you get more digits. That's one reason I like to use calculate. So I do stat, tests, z-test. I'm going to run all the same thing but choose calculate. And it just gives you the numbers, but it has space to give you a lot more digits. So it shows you we had our alternative hypothesis mu was not equal to 0. Our test statistic is 1.2 something with a lot of digits, and our p-value was 0.2 something with a lot of digits. And it also summarizes there x bar and n. So that's how you get the test statistic and the p-value. So again, you need to be thinking about this as we go along. We're going to get more and more procedures. So in the context of the problem, you have to decide, okay, what's my hypothesis? In this case, we've got that the mean difference is equal to 0 versus it's not. And then you have to decide, so what's the appropriate test? Well, we know sigma, and our hypothesis is about a single mean. We're going to use z-test. And then you get your test statistic and your p-value, and it's customary to report those two things. And then you make your conclusion. Okay? So a problem may give you a different alpha, but if not, we're going to go with 0.05. If alpha is greater than 0.05, or if the p-value is greater than 0.05, which it is in this case, our generic conclusion is we fail to reject the null hypothesis. Okay? We failed to find evidence to say that mu is not equal to 0. Okay? Maybe it is, maybe it isn't, but we didn't have enough conclusive evidence to reject the null hypothesis and conclude that mu is not equal to 0. So on the notes, I have the screenshots and then summarize. There is not significant evidence. Either there is or there isn't significant evidence to reject the null hypothesis. There is not significant evidence that job satisfaction differs between machine-paced and self-paced. So you see I've written a contextual, real-world explanation in my words, and you use whatever wording you want, but it's got to have that basic meaning. We did not find significant evidence to conclude against that the difference between job satisfaction was not equal to 0 here.